All right. So I kind of misled you the other day. I said I was going to try to get the exams done, which I did. And then I said I was going to post the grades as soon as I got them done, but it was late last night and I kind of forgot till half hour ago. So I just posted the grades to Moodle, so they'll be up there. Passing out exams today, and I'll try to have them for anybody that is not able to make it today, can get it later. Try to have them with me at least the next class period or two. So you can see the exam distribution. The grade distribution is really pretty awkward this time. It's a kind of opposite of a bell curve, inverted curve here. Surprisingly, a lot of people got really good scores. So there were plenty of A's, and most of the A's were close to 100. Not very many B's overall, a lot of C's, and then a lot more than I'd hoped for less than that. So at first when I was grading, I had some pretty serious concerns that the average would be a lot lower, but there were actually quite a few of you that did pretty well. So generally, if the average is kind of near a, upper 70s, lower 80s, that's pretty typical. So I didn't do any curving or anything, but I will keep it in mind that I know that, for those of you who particularly struggled, one thing that can happen is, you get stuck somewhere and it propagates through the rest of the exam. So I have a lot of sympathy for that. So if I do end up making another exam that's pretty difficult, I would probably curve that one. Otherwise, I'll say we should discuss if you have a particular concern or felt like you were particularly not well represented by your performance here, we can talk about it. But yeah, so all right, so that's what I have to say, kind of big picture about the exam. I'll pass them out in just a moment. I also have a note taker form. I'm very sorry, I've been meaning to read this out and offer this for a couple weeks now, but there's somebody that's interested in having a note taker. So if anyone is interested in providing a copy of their notes for this class to a student with a disability, please take this form at the end of class for further information. Student volunteers need to be in good academic standing and will be eligible to receive one of the following two incentives in compensation. Should be advanced class registration or a letter of recommendation from Disability Services. Okay, and then carbonless paper and or copy machine is available at no cost to the note taker at Disability Services. So if you're interested in that, please let me know. Again, my apologies for the delay there. All right, so I'm gonna pass out the exams. Please be patient with me with names. I don't know everybody. Probably can't by the end of the semester know everybody. I'm gonna try to get to know you a little better. At least name to faces, right? And I'm not the greatest with Louisiana names, so just feel free to correct me, laugh at me, but do so in a way where I can learn about it, okay? All right, so here we go. Braden Fishy. Brennan Bates. Richard St. Martin. Justin Simmons. Chris Dufresne. Carson Caruso. Omar Sermini, sorry. Nolan Brock. Colby Koslowski. Joseph DeFranca. Sean Hunter Cotton. Wandel Bem. May Andre Gideon, Tyler Tran, Morgan Blades, Garrett Petro, Ricky Nguyen, David Minter, Ethan Robson, Britton Overby, Michael Landry, Chloe Beals, George Zwanga, Paris Duvernay, Colin Shortus, Luke Rao, John Alicani, Gabriel Agungu, Samuel Latina, Jonathan Gallagher, David Weathersby, Madison Booth, Patrick Kilgore, Michael Ingram, David Woods, Kenneth Wong, Courtney Halsendorf, David Thomas, Anna Johnson, Naaman Stewart, Kayla Perro, Caitlin Russell, Colin Martin, Brendan Smith, Tatum Bundura, Grant Brown, Landon Hebert, George Massett, Joshua Ford, Grant Jacobs, Avian Delasovor, or Javi, Mia Arzmendi, Crew Matthews, Zachary Michelle, Ava Counts, Samuel Daigle, Tyron Bridges, Vu Tran, Lindsay Hudson, Baron. Hunter Gideon. Darren Ferrisburg. Eli Patton. All right, anybody not have theirs? What's the name? Chance. Yeah, so I will be preparing a homework shortly. It'll be due the day of our exam review, so I'll pull up the syllabus real quick to kind of give you one other update here before we get going. So on the 26th, I'm going to reschedule this a little bit. So I have I'm going to have a guest lecture for you probably here. I may switch around stuff a little bit because I may give this myself, the Flint water crisis, on the 24th, and then this would be a guest lecture on advanced oxidation processes on the 26th. Regardless, we'll have our exam review on the 31st, and we'll have a homework due that day that'll cover basically kind of all the exam 2 sections. So it'll be the filtration, so granular and membrane, and disinfection. No, not planning to move the exam date. I just have I'll actually be on campus on the 26th, but I'm committed to a panel review session, so I'll be on Zoom like 8 hours that day. So that'll be, that's kind of just looking forward a little bit. So you'll have a homework due on the 31st, exam on November 2nd. Yeah. Okay, so with that, I want to make a couple comments real quick on kind of how I was grading this, and then go through, answer any questions, kind of explain how to do the problems in case there are questions here. All right, so in general, if I saw like a tiny mistake, like you missed a negative sign or accidentally moved a decimal place 1 point over and everything else looked correct, but that was the wrong thing, that's typically like a point, maybe 2 off, about 10% of your grade there. If I see you were supposed to do a mass balance on a CSTR, but you tried a batch reactor or something, it's a core conceptual error. But you did everything else right, you'd probably get something like 3 to 4 points off, about 20 to 30% of the points for that section of the problem. If you're making multiple ones of those, it's going to be, if there's like several major errors like that, maybe you got half credit. If I saw you were still trying, kind of in line with how you ought to approach the problem. If you just showed me that you kind of knew what formula maybe you needed to use, maybe you'll get just a little bit of credit just for if that was the only thing you put on there. So that's kind of the general scheme I use. So if you find that something just doesn't feel right, is not adding up, you thought you got a lot closer than I marked you, you're welcome to talk to me about that. But in general, that's my aim, is to, in a consistent manner, give partial credit according to what I see you've learned. Right, so if you show me what you learned, then I can do something with that. All right, so I'm gonna dive into it. Feel free to stop me with questions, and I'll kind of talk about how I solve these things. Yeah, and I've got a question online. You're welcome to come by, and I'll get to you in just a second. You're welcome to come by if you didn't get your exam. I will be in my office for the rest of the afternoon. Welcome to stop by, and I'll try to have them with me for our next class as well, maybe the next 1 or 2, to have them there for you. Yeah?
I don't know if I missed it, but are we keeping exams?
You can keep them, yes. Yeah. Yeah, so you're welcome to keep them and deal with them. If you are going to make some sort of changes, like at this point, just for your own sake, use a different color ink or something. If you're going to come back to me with questions, especially. All right, so what's the name? I'll get your exam. Okay, 1 second. I'm about to get started here. All right. So problem 1 was essentially ionic strength equation, kind of at the very basic level, a mass balance in the swimming pool of sorts, just that we have some volume of water, it's 80,000 liters, and we were adding salt to it and just kind of checking on what resulting ionic strength would that yield. So in the first case, we have 500 kilograms of sodium chloride, and it says it will completely dissolve. So that means we'll have NaCl dissolve to make Na plus and Cl minus. Okay, so then when we are aiming for our ionic strength equation, that's going to be equal to, we've got the formula. I'm going to write it this way, say 1/2 times the concentration of the sodium times its charge squared plus the molar concentration of the chloride times its charge squared. Okay, so that's kind of fundamental there. The other aspect is we need to figure out what molar concentration do we have for each of these. So we can kind of take a look at what molar concentration of sodium chloride did we dissolve in the first place, and that'll be a 1-to-1, because we can say that we have 1 mole sodium chloride going to 1 mole of sodium and 1 mole of chloride. We can relate that equal to the molar concentration of both the sodium and the chloride, right? So that's kind of the fundamental process we need to do. And in order to find that molar concentration, we need moles per liter. And so we are given some amount of kilograms and 80,000 liters. So we'll take this 500 kilograms, multiply that by 1,000 grams per kilogram, get that into grams per mole. The other thing we need to do is look up the molecular weight for sodium chloride. That would be from our periodic table, and we could add them together and see that should be 58.45 grams per mole. So if we take this 500 times 1,000, so 500,000, and multiply that by 1 mole per 58, basically dividing by the molar weight, right, molecular weight, excuse me, by 58.45 grams, and take all of that, divide it by the 80,000 liters. That should give us a concentration for either of these at 0.01693 in moles per liter. Okay, then it turns out in the case of ionic strength with a +1 and a -1 here with equal concentrations, you'll notice 1 squared and -1 squared, that's just 1. So it's really just 1/2 times the one concentration plus the other. So in a very simple case, for doing sodium chloride, we find the concentration. It turns out that's equal to the ionic strength. So that would be 0.01693 as our answer. All right. Same thing goes for the next problem, part B, except we have a slightly more complicated. We have this aluminum sulfate. Yeah.
Is it actually 0.106?
0.106? Yes, I'm sorry. I had it written that way on one part, and then I miswrote it on another part, and so there we go. So, by the way, please check to make sure that I didn't count you off. I think it would have been fine. Yeah, in fact, the way I wrote the final ionic strength was 0.107. I rounded up. So, should be fine. I just had it written strange in one spot. Sorry about that. Okay, so then the aluminum sulfate, this is something we use for coagulation a lot. If we add the same amount but no NaCl. And this totally dissolves to, so Al2SO4, 3 of those. This will completely dissolve to make aluminum, 3+, and sulfate, 2-. Now, in this case, we could notice that we're going to have 2 aluminums because there was Al2. For every 1 alum molecule, we get 2 of those and 3 of these. So we can again find our molar concentration of aluminum sulfate that we added, and then from there convert it to solve for our components there. So we'll need the molecular weight for the alum. That's going to be 341.37 grams per mole. We go through the same process to find the concentration here. That's going to be this 500,000 grams times 1 mole per 341 grams of the alum. All that divided by our 80,000 liters. So one common mistake was not recognizing that we need to account for the volume of the entire pool. You just kind of assume that it was all in 1 liter. That would give you a very large number for sure. Okay, so then in this case, we can find that. Putting those numbers in, that should be 0.0183 moles per liter. And from here, we recognize we have 1 mole Al2SO4 3 is equal to, or yields, 2 moles of the Al2, Al3 plus, and 3 moles of the sulfate. So with that, we can find our aluminum concentration and our sulfate concentration. And these, aluminum is just going to be 2 times this, and sulfate's going to be 3 times that, very simply. So when we solve that, this one, aluminum should be 0.0366 moles per liter, and this one should be 0.0549 moles per liter. Okay, then we can solve our ionic strength equation, and this should be SO4 2- times -2 squared plus this Al3 plus times the 3 squared, and 1/2 times all that. So when we put in the numbers, this should come out to be 0.275. All right, so that's the solution to that problem. Most of the issues, I think, were related to, if there were issues, were related to not really understanding or effectively finding the molar concentrations that you needed to use. Okay, problem 2, we had this hydrolysis problem, and understandably had some confusion here. It had a couple tricky spots that I didn't quite mean to be so tricky, but a fair amount of you did just fine. Okay, so the problem says we have some report that hydrolysis of iron can be modeled as a first-order equation, and then we're given some info, batch experiment with pH 3.65. 20% of the initial iron is hydrolyzed after 15 seconds. And then it says, assume this reaction will act as a forward, irreversible reaction. Part A says, how long will it take before 99% has been hydrolyzed? Okay, so the first tricky part here could be that if you're thinking about it and you think, okay, 20% there, you might start thinking 20% remaining, but this is actually 20% transformed, right? Or hydrolyzed, whatever. Whereas, so we're looking to get to 99%. So in the 20% case, 20% has been changed. That means there's 80% has not been changed, right? Unreacted or unchanged. So when we talk about our C over C naught, what we're talking about in the case of what was given to us, that's 0.8, or 1 minus 0.2 would be another way to say that. Okay, that's what the piece that we need to find the reaction rate constant. So this was the core principle of the problem that you needed to be able to recognize is you were not given a reaction rate constant, and you needed to find it given the information provided. Now, speaking of information provided, the fact that we have some pH is totally not important. So you could kind of just ignore that altogether once you realized it's just a mass balance problem. So this component was really, we have to deal with this to find a K in order to answer problem part A. So if we recall in a batch system, we could describe it as V dc dt equals negative K C, negative Kc in the volume. Once we separate and integrate this becomes the natural log of C over C naught equals negative Kt, right? So from here, we can solve for K because we have a known time associated with a known ratio of what's left. So with this, we can solve for K by saying the natural log of 0.8 is going to be equal to this negative K times 15 seconds. So one thing I was looking for is to see that you were able to solve for the K. That should have been 0.0149 per second. Right. So once you've done that, then you can come back to this to solve for time instead of solving for K in the new condition where 99% has been hydrolyzed. That means what's remaining compared to what we started with would be equal to 1 minus 0.99 or 0.01. Right. There's a fair amount of people that were flipping this, and it does get a little confusing with the way we look at our coagulation problems, which we had one. We go C naught over C, and it gets a little bit backwards there. So do pay attention to what this is really referring to, the current compared to the initial. All right, so with that, we can solve the natural log of 0.01 equals this minus K, which is now known, 0.0149 seconds to the minus 1, times the time that we're looking for. And when we solve that, the time should come out to be 309 seconds, or about 310. Okay, so then in part B, we're asked, well, what about a CSTR? Kind of the same conditions, but we have instead a CSTR case where we have some flow coming in, some flow leaving. This thing's got some volume, it's mixed. We have C naught coming in, and we'd have C going out. And we would assume at steady state, it says that to us. So we're going to use the same K. So given this reaction that was described, the K won't change depending on what container it's in. So this K is still going to be whatever you found in part A. And I tried to take a look to see if you had kept that. If you had found a K, even if it was the wrong one, if you did something wrong in part A, if you had the rest of this process correct, then you would have gotten most, if not all, the credit here. So then setting up a mass balance, we could essentially solve this for the residence time that we're looking for, right? So a mass balance would say what's coming in is equal to what's going out plus what's reacted. Or we could say 0 equals QC naught minus QC plus this reaction term V minus VKC. To get it into a residence time, we can divide everything by Q. This will give us C naught minus C minus theta KC. And now the next part, I would like to get it into a form where we can compare this ratio of C and C naught. So I'm going to go ahead and solve for C over C naught, or some arrangement of that, and then solve for theta. You could solve for theta directly and then do the algebra to get into a manner that you can compare C to C naught. That would be fine too. Algebraically, we'll come to the same conclusion, but I like to go from here to get C over C naught like we've done in the past. So I'll add the C terms to both sides, C plus theta KC. This equals C naught. Divide everything by C, and we'll get C naught over C is equal to 1 plus theta K. So this is kind of 1 over, if we know that C over C naught needs to be 0.01, then we know that C naught over C, if we invert that, 1 divided by 0.01 equals 100, right? So it's 100 times, what we started with is 100 times more than what we ended with, is another way to say that. So that's fine when we can work with it in that manner, and that actually makes it really easy to solve for K, or excuse me, the theta. So we'll say theta is going to be equal to, and I'm just going to go ahead and write in 100 here. I'm going to say theta is equal to 100 minus 1, so 99, divided by K. And we can solve for that and say theta should then be 6,655 seconds, or basically 111 minutes. All right. So if you were in that direction, hopefully you should have gotten most of the credit there. Does it make sense? All right, part C. We have a question that says, well, what about 2 identical CSTRs in series? Now, I realized during the exam that that was a lot more vague than I meant it to. So I'm accepting an answer that would be either the residence time for one of those chambers or for both combined. Either of those is an acceptable answer to me. I rewrote the question to say, what is the total residence time required for 2 identical CSTRs in series? But on our exams, it says just what about 2 identical series? Either way, we have to take the approach where we say, well, we've got a system that looks like this, where we have some C final, we'll call that C2. We've got C1 that's coming out of the first chamber and C0 going into it, or C naught. Now these chambers are the same, and so we'll say theta 1 would be equal to theta 2, also meaning V1 is equal to V2 and all that. So we have some flow rate going through the whole system. The way to consider C2 compared to C naught, this is what we're asking for, right? We need this to be equal to 0.01. Now, in order to find that, we break it down into the individual mass balances. And this part, really, we just have to look at it from an algebraic standpoint, right? How do we, given that we can find C1 over C naught, and we can find separately C2 over C1, because we've learned how to do mass balances at this point, we can do each of those individually. Then what algebra does it take in order to get things to cancel? Well, you have to multiply those together, right? So the C1s cancel. That lets you leapfrog from kind of over the C1 challenge there. Okay, so that means if we get, and because they're identical, it's going to simplify even further. But let's just say for one of them, C1 over C naught, well, we know that should be basically what we were deriving a moment ago, right? This term here, if we just invert this guy, it would be 1 over 1 plus theta k. And we've seen that 100 times now, right? So this should be 1 over 1 plus theta, I'll say theta 1 k. K is not going to change between them. And since we said theta 1 is equal to theta 2, then we're good. All we have to do now is multiply this by the C2 over C1, excuse me. And so in this case, what that will look like, so I'm sorry, let me slow down. In order to get, I'm just going to write it this way. We know we have to multiply the two, and if we take a look at C2 over C1, that's going to be the same exact thing if we do the mass balance. It's a mass balance on a steady state CSTR. 1 over 1 plus theta k. We'll say theta 2, but since they're equal, we can then say theta 2 over C naught is equal to 1 over 1 plus theta k multiplied by the same exact thing because the thetas are the same, so we could just square it. From there, we just need to solve for the theta and do the algebra to do so. And we also recognize this is equal to 0.01. So I'll take the square root of both sides and say square root of 0.01 is equal to 1 over 1 plus theta k. And then we can say theta k will equal 1 over square root of 0.01, all that minus 1. And so we just divide both sides by k, and we get theta is equal to 1 over square root of 0.01 minus 1, all that over k. We had the k from the beginning. So again, what I was looking for is for you to go through this process to solve for theta. So even if you're using the wrong k, but I saw you do this, maybe I didn't take any credit off if I saw this process. Okay, with that we can solve, and theta, I'm going to say each theta in this case would be 605, basically 604.99 seconds, or basically 10 minutes. And then that would be for each, or if you gave me the total, which I'm not sure anybody bothered to do, which is fine, would be twice that, right? Because there's two chambers. So 1209 seconds or 20 minutes. Any of those I found acceptable for the problem. All right. And by the way, we can compare that because this is kind of the point of the whole process. 110 minutes, 111 minutes compared to 20 minutes total is a pretty significant change, right? And that's all by just splitting the volume into two separate chambers and doing them one after the other. All right, so problem 3, we have, this one's a sedimentation type of problem, and part A starts out with kind of just a mass balance on a rainfall, say what kind of volume are we producing if we get X amount of rain over some amount of territory. So it says we have a construction site, we are essentially digging up a lot of sediment, and we need to protect local streams from runoff. And so if we have a 1.5 square kilometer area that receives 5 centimeters of water over 8 hours, what would the flow rate of the runoff be in cubic meters per second? So we're just really looking at essentially some sort of a rectangle, right? And then we can imagine a very thin height on top of that for the rain that's added to that area. So we can get some volume based on this box. And so we know the area here was given, 1.5 square kilometers. We can convert that to square meters. That would be 1.5 times, let's see, we'll do the conversion, 1.5 kilometers squared times 1,000 meters per kilometer. But we need to square this, right? So that's going to be essentially 1.5 times 10 to the 6 square meters. Okay, then we have a depth or a height, I guess we'll say, of 0.05 meters for the amount of rain. So that's some volume we can get, and that should be, let's see, have I done this right? Yeah, so it should be 75,000 cubic meters. And that would be over some amount of time. What was it, 8 hours? Yeah, 8 hours. So our flow rate effectively will be, averaged over those 8 hours will be 75,000 cubic meters divided by 8 hours times 3,600 seconds per hour. That should give us a value of 2.6 cubic meters per second. All right. So that one was, more like just a word problem there. All right, next we are told to design a retention pond to act as a basin that should be able to handle a flow rate of up to 2 cubic meters per second of water. Now you'll see I just gave you a new flow rate, so you didn't have to rely on part A. Whatever happened on part A would not affect this problem. It's just kind of a reference point of what a storm might do and what kind of a flow rate that might provide in this scenario. Okay, so then we need to remove all particles above 20 micrometers in diameter. And the question is how much land area must be set aside for the sedimentation pond for that. And we assume we're given that the temperature is 15 Celsius and the particle density is 1.55 grams per centimeter cubed. Okay, asks for the answer in square meters. All right, so this problem we're going to need to solve for a sedimentation velocity. We know that has to do with the gravity times the rho of the particle minus the density of the water times the diameter of the particle squared over 18 times the dynamic viscosity. So we've got that, and we can solve for that specific particle. We've got a few parameters here. If we look up, the mu should be 1.139 times 10 to the minus third kilograms per meter second. Our rho of the particle, this 1.55 grams per centimeter cubed, we should be able to convert that to get 1,550 kilograms per cubic meter. We need everything in kilograms and meters and seconds here. The rho of the water, we can look up and see that that's 999.1 kilograms per cubic meter. Flow rate was given, and our diameter of the particle would be 2 times 10 to the minus fifth meters, or 20 times 10 to the minus 6. Okay, so with that, we can say, we put all those things in, the settling velocity should be 1.054 times 10 to the minus 4 meters per second. So that's one thing I was checking to see if you had all the unit conversions and things put in appropriately. And then the next concept was the fact that we need to design our basin area based on essentially that concept where the particle has a certain amount of time to fall, right? So we have this settling velocity, and we're going to equate that to a design velocity which tells us the ratio of Q over the area of the basin. So we know the Q, we now know the VS, which means that's how we're designing it. And we can solve for area of the basin as this flow rate, which is given divided by the sedimentation velocity. So this should give us 18,968 square meters. All right. Any issues? Yeah. Yeah. Does it make sense? Got a question? You good? Or you got any questions? Okay. Yeah, so that one was really like some amount of rainfall. We are treating that as a flow rate, you know, kind of averaging over the time that it was there. All right, so last problem. I regret a little bit how I formulated the what I was hoping to be a little helpful for both of us is this part here. I realized later that I accidentally kind of misled you. So if we read the problem, first of all, I should have went ahead and put a spot for what the question was actually asking for, which is the collision efficiency. Would have been nice. And also, part C here was given to you, so that was possibly a little bit tricky if you didn't recognize that that was given and you had to solve for it. So didn't mean to confuse you, but there was a little bit of trickiness there. So this one was given as 12. That's given in the text when we say the aggregates leaving this basin each comprise 12 of the initial particles. That means there are some number of initial per every final particle. That would be a ratio of 12 to 1. Okay, and so that was, as we've covered in class, that's important to recognize that, and that's where that part C would come through. So we need to solve for this alpha, this collision efficiency, and there's going to be a lot going on here. Yeah.
Can you explain to me again how you got 12?
Yeah, so that's coming from this line right here that says the ones that are leaving the basin, the aggregates leaving the basin each comprise 12 of the initial particles. So what we're talking about there is, like, if we're treating this basin kind of like a CSTR of some sort, you know, maybe it's a river bend, but it's mixing well enough. What we're looking at is some number concentration coming in and some amount leaving. And even if we have billions and billions of particles, the ratio between that number and the final number will mean, like, if they're sticking together, that means we should know something about, like, we started with this amount per volume, and then we ended with one particle that was comprised of, you know, some number. So if this was, let's say, it looks like 7, and this is 1, this would be 7 per volume, and this is 1 per volume, and we could look at it like that, right? So then n naught over n would equal 7. Yeah, so that's the way we're describing it there, in order to make that comparison. So that was part of it. Yeah, so we'll leave that. I think I've got more space to solve this too if we need. All right, so that was kind of one of the major components. The other piece was to recognize that we need to find this alpha, and in our minds, we might be thinking, oh, well, we know where alpha can be found. It can be found in K, right? K should be defined by 4 times this alpha times omega times G. G was given, all that divided by pi. So a couple things that were given, the mixing intensity here, that was 205 per second. We were also given N naught. It's 5.5 times 10 to the 6 particles per liter. And the diameter of the particles was also given. I don't think we needed that in this problem. Okay, so a couple other things we know. We do have a flow rate. Very large flow rate, times 10 to the 4th cubic meters per second. That's a lot of water. Okay, then we also, at this temperature, we have our dynamic viscosity as 0.89 times 10 to the minus 3rd kilogram, excuse me, that's kilograms per meter per second. Okay, so then when it comes to solving for this alpha, one thing we have to realize is we actually don't know K, and we need to find K in order to be able to solve this problem. So we need to rearrange this to solve for the alpha. In fact, we'll go ahead and write that up. So we could say alpha is going to be equal to, if we multiply both sides by the pi, so we'll have K times pi divided by the omega times G times 4. So that will be a way to solve it rather than finding K assuming some alpha. Since we're out to solve for the alpha, one thing we recognize is we actually can solve for K with a mass balance equation because we know something about the outcome here. So that was the tricky part. Some people were like, well, I don't know how to solve for alpha. Maybe I have to get a K first, and so I'm going to assume an alpha, and then, it ended up getting a little bit backwards because in order to solve for K, the best way to do that would be to do a mass balance to say we've got some amount coming in, amount going out, minus VK N, right? We know the ratio between N naught and N, and so we can solve for this K if we do it that way. So we can divide everything here by Q. That'll be N naught minus N minus theta Kn. And if we solve this for K, we should, just like we did a minute ago, we'll get to a point where we say 1 plus theta K equals N naught over N. We divided everything by N and changed sides with things. So then K, in this case, should become this N naught over N minus 1 divided by theta. It's not going to let me write it. There we go. And we can find a K value that is 0.123 per second. So once we have that, then we are just about ready to solve for the alpha there. So we could go ahead and write this 1, 2, 3 seconds. Now, the last piece we need, and maybe you solved this earlier, would be this omega term, the flock volume. Remember, this term is the portion of the water that is occupied by the particles. So it can never be above 1. So if you got a value that's above 1, you know you did something wrong with probably the units. We do have an equation for this. This should be the N naught times the diameter of the particle, so we did need that. Excuse me on that, times pi over 6. if we convert the diameter to meters, and importantly, the liters here in the and not to cubic meters, then this should come out to be 1.77 times 10 to the minus third as a ratio. Okay, with all of that, then we can solve for our collision efficiency, and this should come out to be 0.267, or about 26 to 27%. All right, does that make sense? All right, any questions or issues? How do you feel about it? Okay, maybe okay. All right. Okay, so I think that's all I'm gonna do for today. So let me know if you've got questions. We'll see you on Tuesday for some disinfection, if not.